Okay, ladies and gentlemen, welcome to the Innovation Stage at EMO 2025 in Hanover. We're looking at innovation here, and we have the last item on the agenda today, the very last item on the agenda of our wonderful agenda for the entire week. And now we're going to look at a subject which couldn't be more forward-looking. It's right now something that's the talk of the town, CO2 footprint of machines. Why is this important? Everyone's talking about sustainability. It's very, very important to do life cycle assessments, to look at how large our footprint is when we produce machines. And the important thing then is that we have to have the possibility of generating transparency across the entire life cycle. And one person who deals with this very intensively at the most important association in the industry, this is Ralph Reines. He is the expert on research and technology at the VDW, and he's going to be talking to us about the method for determining CO2 footprint of machine tools. Ralph, over to you. Thank you for those words of introduction. It truly is the very last presentation at the entire EMO trade show. Why is that the case? Well, it's because we always save the best for last. It's about CO2 footprint of a machine tool. How can you determine that? We've given this some thought. It's important to think about it, and for that, we got some help from Professor Hackel at the University of Cologne. We asked him this, and he said, what you're planning to do there is impossible. And nevertheless, we were able to convince him to come on board, and he said at the end, wow, we did it. Now, what exactly was the job to be done? Well, how can I, a manufacturer of a machine tool, determine and calculate the footprint, CO2 footprint of that machine at an acceptable level of effort and expense? On the one hand, it's important because customers of machine tool manufacturers, that is the companies that buy the machine tools, they ask about the footprint. They want to know how big the CO2 footprint is. And probably this is something that will have to be indicated as part of the digital product passport. That is the regulatory side of things. The EU will demand it. And last but not least, it's a contribution for companies to do self-reflection. They want to know themselves how big their carbon footprint is, the footprint of their machine tools is, and how they can reduce it. That would be the next step. And what's the backdrop to this? Well, greenhouse gases cause climate change. Unless our name is Trump, we believe that that's the case. It's proved scientifically. And as a company, you've got to already know your own CO2 footprint, but not for the product, but the company. You do already have the corporate carbon footprint. The CSRD prescribes this. And now it's about the footprint of the product for machine manufacturers. It's thus the footprint of the machine. Then we, the association, we're here for the members, and we said if we've got to do it, then we are going to develop rules as to how to do this in a standardized fashion so that everyone does it the same way, and we thus achieve a certain level of comparability. So an industry ought to always work on the basis of the same rules, and in standards we talk about product category rules. That's what they say in the field of standardization. Now, what are the challenges in this context? Well, that's what we see here. Everywhere around the trade show, you never see two machine tools that are the same. There's big ones, small ones, some do milling, others do turning, EDM machines, lots of different technologies. They're complex. They consist of many thousands of individual parts, maybe even many tens of thousands of parts, and so on. Moreover, there's dry metalworking, wet metalworking, different materials are used. Alloy is soft, titanium is hard. What if your tool is dull or sharp? Does that have an impact? And so on and so forth. And above all in the use phase, if I'm a machine manufacturer, well, when the machine is being used, I can't even impact it anymore. I don't even know how my customer is going to operate it. Do they do highly automated mass production in 3 shifts, or maybe there's a lack of parts and the machine is at a standstill for a long time? I'm the manufacturer and I don't know that afterward. So, the product group is very heterogeneous. I've got an example, it's over there. It's from Chiron. That was the previous speaker talked about watch production. And this is a machine that you can use to mill housings for wristwatches, a milling machine. But they also do milling here. Gears for windmill turbines. You've got the gondola at the top, and the gears have a diameter of 10 meters. And I'll give you a comparison. If you, when you drive home, well, when you go through a tunnel, they have gears of 8 meters. This is 10 meters, and this too is also a machining center. This is Schule. It's big as a soccer field. Now, these are the challenges we had. How can you put together rules that apply to all of these machines? Then there are even more challenges. That is the environmental challenges. Emission factors for individual parts and processes are not standardized. There are many different databases from which we can take this information. And even if you have the same material in different databases, you often have different numbers. And it's not a difference of just 10%. Sometimes it's a factor of 2 or 5 or even a factor of 10. Now, in principle, we can say that the best thing that can happen to you is you just ask your suppliers. You buy a part somewhere, you ask the supplier, hey, what's the emissions for the part that I buy from you or from the material I buy from you? However, unfortunately, as of 2025, frequently, you can't get that number from your supplier. But it would be nice if that were the case. If you have it, you take it, of course. This is what we call primary data. Now, what do you do if you don't have that data? You have to use secondary data, which means you've got to calculate that number yourself, and you do that by doing the following. On the one hand, you look at the activity data. As a rule, how heavy is the part? What's the mass, the weight? Then what's the material it consists of, and then you find the corresponding emission factor for that in a database, and then you can calculate it. And all of these things were the challenges. How did we solve this? Well, product category rules that apply to all machines regardless of the technology. And then, for our members, it should provide a simple and practical approach, easy to implement, with a reasonable level of effort on the one hand, but on the other hand, they should also provide good results. We don't want to do greenwashing. And in this way, we're making a contribution to what everyone's talking about. Lawmakers are always asking about it. It's a contribution to eliminating bureaucracy. We're not really eliminating bureaucracy. You have the rules and regulations that are still there, but we offer a solution for how, even for an SME, you can implement that well. And when I say we, well, who developed it? We, the association, VDW. We did this together with 6 of our member companies: Chiron, DMG Mori, Grob, Heller, Schuler, Presses, and United Grinding. And we got scientific support from the University of Cologne, Professor Hackelöhr, and his initial statement there was, it was impossible, and we did it nevertheless. And after about a year, we got the result, and it looks like this. We wrote a VDMA standard sheet. The title is Product Category Rules for Determining the Carbon Footprint of Machine Tools and Machines for Additive Production. We included them too in this. That's the VDMA specification, and it took us 6 months in order to prepare all the content and develop the method. And then there was a commenting period, lasted half a year. That's the way it is for VDMA It's almost like a standard. And then all of the comments that were sent in were incorporated, and it was then published in April of this year. So how does the method look? Well, first of all, you've got to know that the life cycle of a machine tool begins when you design it. You purchase the material, and then you produce it. At some point in time, it's done. It's at the shipping ramp. It's shipped to your customer. There it is commissioned, and then it is used, put into use. That's when the use phase begins. And then at the end of the day, or at the end of its life, it is recycled. And if you want to see that on a chart, this is what it looks like. For an entire life cycle analysis, you'd have to have 13 different impact categories that you look at, and we focused on the first one, the greenhouse gases, because that's the most important one for us, and that's the one that's being asked about. And that goes out and is expressed in CO2 equivalents. So what's the first thing you do? You first of all define what you're considering. What machine am I considering? Am I looking at? That's the first step. That's the declared unit. You've got to define that. And then for that declared unit, I have a look at what the whole thing weighs. What does the switching cabinet weigh? What do the motors weigh? What does the rest weigh? The overall machine that is minus switching cabinet and minus motors. Why do I look at the switching cabinet and motors separately? Because that's where the critical raw materials are. Gold and copper and rare earths. As you know, synchronous motors have magnets, often permanent magnets. There you have rare earths in there, and you shouldn't neglect those. The weight might be small, but they have very, very high emission factors, and that's why you should always look at them. And if you then look at the details of that, you see that you've got almost everything that you need there for the first life cycle phase. You know what the parts weigh, and if you take mass times the emission factor, then you know the emissions for the material. In this case, it's for the switching cabinet, the control cabinet, and then for the motors. And for the individual parts, well, what we do is we use a bit of a trick. It's a mathematical process. We use the Pareto principle. We take the parts of the machine, we sort them, first part at the top, or the heaviest part at the top, the lightest part at the bottom. Even if you have 10,000 parts, you'll notice that 80% of the mass of the machine is in less than 20 or 30 parts. And this is what makes this method practical. It's not that much effort and expense, and nevertheless, you get a precise result. So for the heaviest parts, well, mostly the heaviest part is the machine bed. It weighs a couple tons. You take that, mass times emission factor, maybe it's a casting or polymer concrete, and that gives you the emissions of that material. And then you repeat that until you've covered 80% of the weight, and then you scale from 80 up to 100%. We shouldn't forget that we have to have 100% of the mass or weight, and then you have a bit of a safety margin that you add so that we can't be accused of greenwashing or suspected of greenwashing. And then you have the footprint for the entire material. That's the first life cycle phase, and that's the most difficult one. So if you've done that, you've done most of the work. Now, you have all of your material there, and what is the main job for a machine tool manufacturer? Well, they take the individual parts and put together a machine. How does he do it? Well, he does it in the company, and what we do is quite simply say this: okay, dear company, you have a corporate carbon footprint that you've got to calculate anyway. That's determined in the CSRD directive, and you've got that number. Those are all of your emissions in the company for an entire year, and now you just distribute that to the number of machines produced, the number of machines you manufacture that year. And you can do this allocation either by doing it by means of weight or by means of productive hours, or you can do it in monetary terms. And then You've got the carbon footprint or the emissions for production, and if you've got those two and you add that together, material plus production, because then the machine is ready to be shipped, that is the footprint for the machine cradle to gate. That is, from the cradle to the gate of your factory before it's shipped. And then it's shipped out. Shipping, transportation of a product, including for a machine tool, is quite simple. From a CO2 point of view, you take a truck and you drive it, bring it somewhere. Maybe you use a ship-to to transport it, or maybe you transport it by a train. There are lots of good calculators on the internet. You can enter the mass and you say where it starts, where it goes, the destination, and the calculator will calculate it for you. It's very easy. Then commissioning the machine tool. For a standard machine, that plays basically no role at all. You have a service technician that goes there. Maybe he's there a day or two, maybe a week, and then the machine has been commissioned. Now, basically, from an emissions point of view, you only have the emissions for the trip, and you can calculate that like for transportation of the machine itself. And now you have the use phase, and this gets exciting. It gets interesting. How can you make comparable calculations for the service life of a machine tool, and how high are the emissions that are generated if you have so many different types of machines? We discussed this to a certain extent, and we figured this out. We'll define one standard operating hour for the machine. We define a standard operating hour, and we broke this down as follows. If it's off and in standby, it's 40%, and if it's ready for processing, it's 20%, and 40% of the time it will actually be producing components, which, if you do the calculations, 40% off standby, it sounds like a lot, but that's not true. It corresponds to a machine used 6 days a week in a 2-shift system for the entire year. So that's the breakdown of the different operating statuses. Now, what are the most important energies that go into the machine? Electric energy and compressed air, the electrical connection to the machine, that says it on the ratings plate for the machine. And there are many research projects that have been done in the framework of energy efficiency. They started 15 years ago. And on the basis of all of these, we can say in the processing status, about 30% of the connection power is used. So you just have to read the ratings plate, 30% of that, and then you know how much energy is used in that standard hour in the machine. And you can do the same thing for compressed air and for the other statuses. And then you have the emissions for 1 hour of machine running time. That's what you've calculated. It's 1 hour. That's a good comparable value. But you've got to know how high the emissions are for the entire use phase. And for that, we have stipulated this. The use phase of a machine, the reference service life, is 25 years. Now you can have heated discussions about that. A lot of people said, our machines run a lot longer than that. Okay, we've set it at 25 years. And that means it's standardized for everyone. If you want to do it more precisely for your machine, you can use a different value. In terms of the method, we've established 25 years. 25 years, that's 219,000 hours. So if you take a standardized hour and multiply it by 219,000, you get the emissions that come from the machine during the entire use phase. And then you just have end of life left over. At the end of the life of the machine, the material that goes into the process has to be recycled afterward, and for that there are emission factors. So what you do is you just take the material that went into it at the beginning, you take the corresponding emission factor, and then you get the emissions for the life cycle phase that we call end of life. And you're done with your calculations then. And the results look like this. For each and every one of the life cycle phase, you've calculated, you've determined the emissions, and if you add that all up, then you have the emissions for the entire life cycle of your product of machine tool. And this chart, I think, is quite impressive. But for experts here, it's not a surprise. Most of the emissions are generated during the use phase, typically far more than 90%. By the way, this chart is correct for the small Chiron mill that makes housings for watches, and even for the big press line from other companies. So we noticed and we found out in our study of the method that it's the same for both. Now, you take the production material, look at that, 1, 2, 3%. So I'm sure you'll agree when I say it doesn't matter whether you have 80% or 90% of the parts that you use for your calculations, even if you do a small mistake. Well, 10% of 1%, that is negligible. And nevertheless, you'll get a good result. So the question is, did we, the association, solve the task that we have established for determining this method? And I will claim, yes. Machine tools are a very heterogeneous product group, but nevertheless we were able to develop a method that can be used for all machines, despite any no matter what the technology, the size, the material that is worked on. And we've reduced the effort and expense to an acceptable level with good data quality, even though a machine consists of thousands of individual parts, which means the effort and expense for companies has been substantially reduced. The results are reproducible because we say, well, you know that you've got to do public reporting, and there you have to describe exactly how you did it and what data sources you used. And we have achieved very good data quality results. So the next question is this something that can be transferred to other product groups? We did it mostly for machine tools that are chipping tools and forming tools, but we also have noticed that it applies to additive machines too. The method can be used there. In fact, in my opinion, since I work for the VDW, I'm responsible for machine tools. Our big brother, the VDMA, they have 40 different sector associations for mechanical engineering, and half of these sector associations say, what you've done is so good, I think we'll use it. Can you explain it to us? And so for the next few years, I've got a very secure job, apparently. What else do we want to do now? Well, we want to cast a glance to the future. Right now, we already have a VDMA specification sheet, but it's not an ISO standard yet. So we've started well, and what we want to do in the next step is take the VDMA specification sheet and come up with an ISO standard. We already announced this to ISO, and they were very grateful to hear about this project. So work has begun there, and in 2028, we'd like to turn this specification sheet that we did into an ISO standard. ISO standards take quite a while for formal reasons. It can't be done that quickly. Now, I'd like to invite you to come and see me at my booth, because I've got a booth here that shows you about this. You don't have to go that far. I'm just around the corner here. Thank you. If you've got any questions, go ahead. Great, let's give him a big hand, ladies and gentlemen. Ralph, thank you. Thank you for that introduction. We do have a few questions here. Let's start with the questions. Now, first of all, when rules are introduced, the question is, how complicated is implementation of it? Because you're on the lucky side with that project. You determine the rules. So how realistic is it for small and medium-sized machine tool manufacturers to use that proposed method without too much effort and expense? Well, that's a great question, which is easier to answer. It's really simple. We've got members that have tried it out, and they told us, well, if our ERP system is okay, you need half a day. Wow, that's great. That's a great answer. Let me answer this differently, in a different way too. We've often been asked, are you going to make a tool out of that? A tool, an online tool, or whatever, so you can provide this for us to calculate it? And our answer is, no, it's just too simple. It really is easy enough to do in 2 hours with an Excel spreadsheet. Great. Now, you talked about the variation of the emission factors in a database. Now, how can you ensure that the results are nevertheless comparable and strong? Well, that's a good question, too. If individual companies use different databases, we really can't prevent this. We thought maybe we should propose or recommend a specific database, but we never do this. As a matter of principle, we say you've got to publish things. You've got to say publicly what database you use. And when you do that, your results are reproducible. Now, in order to make things even more simple for our members, for the most important materials, we informally put the emission factors into an annex, and we took that information from a publicly available database. And the information that we described there is such that without any external means, you can implement the entire method. This can only be a recommendation, though, to use this emission factor. If there's somebody who has a different database or would like to use a different base, they can do that too, of course. Of course, comparability does suffer, that's true, but nevertheless, it's reproducible. Okay, good, thank you. Now, from your point of view, what levers do customers have, operators have, so that in the use phase, and you said it was more than 95% of the footprint, what levers do they have for changing or reducing the carbon footprint? Well, most of the energy that goes into there is electric energy, and that's the question. Where do you get your electric energy? Does it come from a coal-fired power plant, or is it from a hydroelectric power plant? Hydroelectric, very low emission factor, coal-fired power plant, very high. So the number one factor here is, if you're going to do this, you should operate on the basis of green energy. The manufacturer of the machine tool can't influence this. This is up to the user of the machine, the operator of the machine. And the other thing that's completely different from this, independent of this, the more productive your machine is, the more parts you can produce per time unit, and then per part you need less energy, and this of course reduces it too. The part of, well, you can do a productive, efficient machine here, and I think the German manufacturers are the best. Well, this is something that the machine manufacturer can do. And we heard about a fantastic idea from DMG Mori today. So this comes on top. There are technological aspects for taking that very thing into account. Last question, what obstacles are there up to 2028 with up to internationalization with ISO? That's a great question, the best question last. Now, if you go to ISO, you've invited the entire world community to come on board with your work, and we're, of course, not the only ones that have knowledge here. Other companies know things, other countries know things too, they've done things too, and there will be a comment phase, and the content, therefore, of the standard might change. I don't think that the method will be completely jettisoned, but it could be refined and fine-tuned. Great. Well, Ralph, thank you. Fantastic presentation. Thank you for the answers to the questions. Let's give him a big hand. Ralph Ryan, it's a very important subject. Ladies and gentlemen, give him a big hand. Thank you. Thank you.